Welcome to this video. My name is Mark Scythian. The date today is August 11th, 2024. So this video is going to focus on brake horsepower required to accelerate an automobile. So this particular scenario is going to be an automobile accelerating from rest to 1320 feet or a quarter mile or 0.4 kilometers, for which the automobile has a curb weight of 4,850 pounds and the acceleration time goal is 11 seconds. So we can describe this scenario by asking two questions. The first question is, what brake horsepower is required to accelerate automobile from rest to 1320 feet or a quarter mile in 11 seconds? Then the second question is, what top speed does the automobile attain? So the first step is to quantify the vehicle's weight in kilograms mass, followed by quantifying the distance, 1/4 mile, quantified in meters, and then keeping the universal measurement units of seconds for time, in this case 11 seconds. So acceleration is described as distance divided into time squared, which is also equal to velocity divided by time, and the dynamic propulsive force accelerating the vehicle divided by its mass. So we can actually answer the second question first. The top speed or final speed V sub f is equal to the acceleration, which is the 402.4 meters. This is the 1320 feet or a quarter mile divided into the acceleration time of 11 seconds, quantity squared. So this calculates to 3.33 meters per second squared. So if we access the velocity divided by time formula and we solve for the velocity, it will equal the acceleration multiplied times time to compute the top speed of the automobile. So that is 3.33 meters per second squared times 11 second acceleration. So the top speed of the vehicle is 36.63 meters per second, which is also equal to 120.1 feet per second, and also equal to 82 miles per hour. And also equal to 132 kilometers an hour. So next we have to get an idea of the kinetic energy involved in the automobile's acceleration. So kinetic energy, KE, is equal to 1/2 times mass times velocity squared, measured in joules. So we know that 1 joule per 1 second is equal to 1 watt of mechanical power. So if we were to take the kinetic energy 1/2 mass times velocity squared and divide it into time, it would also be equal to 1/2 mass times velocity squared divided into t over 1, so this becomes a dividing fractions application. So 1/2 mass times velocity squared divided into t over 1. So whenever we divide fractions, we have to find the reciprocal of the second fraction and have it multiply times the first fraction. So this becomes 1/2 mass times velocity squared times 1 over t, which can be simplified into mv squared, mass times velocity squared, divided into 2t. So the mechanical power, or the power in general in watts to accelerate an object, is equal to mass times velocity squared divided into 2t, which is measured in watts. So when we calculate the watts to accelerate the vehicle from rest to displace 1/4 mile in 11 seconds, it will equal 134,450 watts of power. And then we know that there are 746 watts of mechanical power to 1 horsepower. So if we divide 134,450 watts into 746, we calculate 180.2 horsepower. And so this is the horsepower, actual brake horsepower, excluding tire rolling resistance and aerodynamic drag. Now, if we include the power, the average power required to overcome tire rolling resistance, we can use the formulation WV times the coefficient of tire rolling resistance. So this calculation, we can use the US system of measure. So we multiply the 4,850 pounds curb weight of the car times the final velocity, 120.1 feet per second. And then when dealing with the tire rolling resistance, or the coefficient of tire rolling resistance, there's an index, but if you look it up, cars and light trucks rolling on level, paved, and dry road will have a coefficient of tire rolling resistance equal to 0.012. So by simply multiplying the vehicle weight in pounds times the final velocity in feet per second times the coefficient of tire rolling resistance, we calculate 6,989.8 foot-pounds per second of mechanical power are required to overcome the tire rolling resistance, but only at the final velocity of 120.1 feet per second. We also know that there are 550 foot-pounds per second to 1 horsepower. So when we divide this value into 550, we calculate 12.7 horsepower at 120.1 feet per second, or the final velocity. Which is 82 miles per hour. So the power to overcome tire rolling resistance at rest is 0 horsepower, or at 0 feet per second, or 0 miles per hour. So this then becomes the average rate of change. So this is the tangent line of the rates of change computation from rest to final velocity. So it becomes a simple average 12.7 horsepower plus 0 horsepower divided into 2. So 6.35 horsepower average is the power required to overcome tire rolling resistance. So then the last part of the lecture is the power to overcome aerodynamic drag. So we can use the standard equation, watts power required to overcome aerodynamic drag, which is the drag coefficient of the car times the projected frontal area times the air density times the final velocity cubed divided by 2. So to set this equation up properly, we can use the US system of measure, but we need to apply the average aerodynamic drag coefficient of automobiles in general, and that is approximately 0.3 on average. So then the average air density from mean sea level to 36,000 feet, including all the different temperature variations, is 0.0023 slugs per cubic foot. And one slug is equal to 32.2 pounds mass. And this is an absolute weight value in the US system of measure. So the slugs per cubic foot value for density and aerodynamics is a very ideal unit set to use for the wide range of degrees of freedom. So our rho value is 0.0023 slugs per cubic foot air density on average. So then the average automobile projected frontal area is a 4-foot height by a 5-foot width times 0.8, which translates to 16 square feet of projected frontal area. And then lastly, we have the final velocity of 120.1 feet per second. So when we compute the power required to overcome aerodynamic drag measured in watts at 120.1 feet per second, it translates to 9,562.4 watts of power, then divided into 746, which translates to 12.8 horsepower. And again, that is at the final velocity of 82 miles per hour or 120.1 feet per second. And obviously, of course, at rest, 0 horsepower is required to overcome aerodynamic drag because there is none. So this again becomes the average rate of change, or the tangent line of the acceleration metrics with respect to aerodynamic drag and power requirements to overcome aerodynamic drag. So this then translates to a simple average 12.8 horsepower plus 0 horsepower divided by 2. So 6.4 horsepower on average is the power required to overcome aerodynamic drag. So when we add all three of these values up, we compute 193 brake horsepower is required to accelerate the given automobile over the quarter mile acceleration time limit. Thank you for watching this video and have a great day. Please subscribe and like for more content.